We're about halfway through our content as well. This is, what is this, chapter 2, right? 2.4 to 2.8. And then we'll be probably getting into more and more applications. So we had 3 sections that dealt with methods of taking the derivative. So they're real technical, skill-based. And so I thought I'd go ahead and review them quickly. Then the last 2 were applications of those techniques, and they involve some problem solving, and those might be harder because they go to various areas of mathematics, geometry, especially geometry. So some things that might not be completely fresh in your mind, not fresh in my mind either, so you have to look back. As far as the homework goes, I was just thinking here, you do have, I changed some setting and I don't know what it was, so I don't know how to change it back. I'm not interested in researching it. But on the homework, you can click on solution and it will give you how to work through it. Hopefully you give it a try first, but I don't think of it, it's cheating. We used to do that all the time. If look in the back of the book, it would sometimes have a few of the steps, get us started. We'd still go back and have to go through it, right? So those are there. So I don't see any big need for a due date where it unlocks the solutions because you already have them. So tonight when I get back, I will move all the homework due date to basically up till the test. So you can still work on them. Again, the goal is that you get through most of it, but there might be a few that are challenging. It gives you that time to fit them in. So we'll just keep doing that. So just because the due date says it's due then doesn't mean you wait till the night before to do it all, because you can't, right? You can't do 3 or 4 weeks worth of work in that time. Okay, so before we start in, let me go ahead and do just a big overview of the product rule, quotient rule, chain rule, implicit derivatives, and then we'll get into it because the others are applications of mostly implicit derivatives. And so as we're going through here, let's see if I can do it in multiple colors. So the product rule, that was kind of the first one we got. And that said, if we had some function that was actually 2 functions, oops, not 2 different functions, sorry. I've been up since 4, so if I get a little bit wacky, more than usual anyway, that's what's happening. Okay, so two functions that are being multiplied. When we recognize that, sometimes that's hard to see because it's not as obvious. Usually there's parentheses around them. Then the way when we go to take its derivative, I guess I should do it down here. What I've been suggesting to do is to kind of come and put the pieces together. So, put your first piece here, your second piece there, and then next to it, take the derivative of the first piece and the derivative of the second piece, because when we go to take the derivative of the sort of whole function, when we have a product rule, I'm going to do it this way. What we end up doing is taking the derivative of the first part and then adding the derivative of the second part, and each of these are multiplied by the other part unchanged. So this is derivative of f times g unchanged, derivative of g times f unchanged. And the text may do it in a different order, but since we've got addition and multiplication, we can do it in whatever order is most beneficial for us. And the reason I go with this order, this is different than the book does, because if I do what the book does, they switch it for the quotient rule because they have to, and that's why I always get confused with it. So I'm trying to force myself to remember it this way. Just take the derivative of the first one, second one unchanged, derivative of the second one, other one, and then it'll be just like that for the quotient rule. I mean, we've had 500 years to get this right. I don't know why they didn't change that a long time ago. But does that make more sense to anyone else? Anyone else have that difficulty of mixing up their left and their right? Okay. Okay, so that's the product rule. We'll put that one there. The other one was a quotient rule, which was, I'll just go with that. And that's when we had a fraction, and we had a top and a bottom fraction or function. So these are a little clearer to see. Sometimes the product rule isn't always clear. But we do the same thing. We just kind of take our pieces. Okay, take the top. Oops, come on. Take the top. Write it down. Take the bottom, write it down. And then take the derivative of the top. Take the derivative of the bottom. And when we go to take the derivative of the whole thing, what we end up getting, and I'll do this, is you get, in the numerator, you get the derivative of the top. We're going to get a minus, and think about it because that one was in the bottom, so, you know, negative, it's like to the negative 1 exponent. The derivative of the bottom, I think I'm getting it right this time. Like I said, this one is always, and then in the first part, the derivative of the first part times the second part unchanged. Derivative of the second part times the first part unchanged. And then in the denominator, you get the denominator unchanged, no derivative in that case, but then you square it. Because think about it, if it was to the negative 1 power, you would have subtracted, you would have negative 1 minus 1, you'll get to the negative 2 power, it would have moved back down. So if you took it more as a product rule, which you could do, you could look at this as a product rule, but it's a little messier, so if you kind of remember this formula, that will help you with anything that's a quotient rule. So far we good? Okay. The main one is the last one, sort of last big rule at least, was the chain rule, where we have a function inside of a function. And again, this might have happened because we've got a square root or a cube root, a radical, and then there's something kind of complicated inside. It could be that we had a parentheses with something raised to a power with, again, something more complicated than just x inside. So there's something inside and there's sort of an outside process going on. So as soon as we spot that, when we go to take its derivative, first part is we're going to take the derivative of the outside part. I'm going to change colors here, I guess. With the inside unchanged. So that's when the chain rule is done properly, you always see that inside part, nothing changing to it. It's still right there. It's just kind of the outside. And again, when I do it, I just actually, if you, like on paper, just cover it up. And I look at the outside structure and I take that and then put that inside in there. And then we have to multiply it by the derivative of the inside. Probably made a poor choice of which colors to do what to, but derivative of the outside with the inside unchanged still, and then the derivative of the inside stuff. Okay, so that's a chain rule. And then the difficulties come when we've got stuff that's like got a chain rule with a product rule in there, or a product rule with a chain rule attached to one of them. We got to do those. So the idea is you practice them enough, it becomes second nature, and then when we get to the application problems, that's where it's going to need it. The more practice you get with these, the smoother things will go as you move forward. And then there was implicit derivatives, which it's hard to get a specific example, but that's when we had two variables, or three in some cases, and it was always, we were taking one way of doing it, say x times y. I'll just do an example. When we took this derivative, we would take the derivative of x, which is just 1. I could put this at a marker d dx that I took the derivative of x times y unchanged. And again, because we've got a product rule going on here, then we leave x alone, and then we take the derivative of y, which is 1, but that one we list as we took the derivative of y but we're taking it with respect to x, because x is our input variable. So we're still trying to see these as functions, even though they really aren't. Or some of them might not be. We got a y squared, it's really not a function anymore, but we treat it with sort of function notation that x is the input. And when we're doing this implicit thing, it allows us to not have to, we could break it into pieces to keep it a function, but this implicit derivative allows us to not have to break it into pieces, and it makes everything work out okay. So that was kind of that one, and the last one sort of comes along from there. So what we have sort of to get us ready for the test, and again, this is all I have either, the coordinators, they've, let's see, are we here? Yeah. So there's this exam 2 review. It's an older one. When I get the copy of the exam, which will probably be the week of the test or maybe just a little bit before, I'll look it over, make sure that everything's here that needs to be there. If there's not, I'll throw in a few extra questions, and you'll know that those extra questions must mean that those type of questions are on the test and they weren't on the practice. But so far, the coordinators, they make the practice, they make the exams, and typically what they do is they've been doing this for a while. They're taking the problems they've always used and just changing numbers a bit, changing them slightly, but the same type of problems. Okay. Okay. Well, that's all I got today. So, what do you got? Any questions? Anything in particular? What would you like to take a look at? We can look at any of these. I think I've got bad memories about that one, but yes, we can. No, I need this one. 2.7 was related rates. Number 8, it's at the end, so it's probably the hardest of the whole bit. Of course, why would you ask the easy ones, right? Oh, yes. Okay. So, and again, just what I'm saying, you can click on the solution, but try to think through it. If you really get stuck, it does give, I could do a selective look at things. I'll look at the solution, but I'll just try to see the first few parts and at least get started. See, we got water leaking out of an inverted, okay, so this should be similar to the one I did in the lecture. We have a tank. That tank was being filled. This tank is leaking. So those are the similarities, and hopefully I can remember what we all did. But we have a rate here. So let's kind of go through and pick out the important things without trying to read too much. We've given our rate here. It's 11,300 cubic centimeters per minute. That sounds like a lot of water to me. And then at the same time, water is being pumped into the tank at a constant rate. Water is leaking out an inverted conical tank, that rate, and then there's some constant rate that water is being pumped in. Hopefully this is also a constant rate. The tank has a height of 9 meters, so that's something that's important. The diameter of the top is 6 meters. If water level is rising at a rate of, so we've got the rate of how fast the water is rising, 16 centimeters per minute, when the height of the water is 5 meters. That's not saying it's always going to be constant at that rate, right? It's just at this particular moment it's going up. Now, if you're thinking of tests, this is probably a very terrible test question, but like I said, I'll let you know what's in there. Find the rate at which water is being pumped into the tank in cubic centimeters per minute. Okay. And then they got a note. So one thing we've got a conical tank. See my drawing skills. Something like this. We know it's 9 meters from top to bottom, or bottom to top. We're leaking out water, so I'll do that from the bottom. 11,300 cubic centimeters. What is the diameter at the top is 6 meters. The diameter, so it's not the radius, so that's good. So D is 6, so what do you think we'll probably need that radius? Probably. So what's the radius? 3, half of the 6. So I better write that, because otherwise I'll use the diameter in the formula. Oops, see, I did it. I said it's 3. Okay, so use the right numbers. Okay, so what we've got, what we know, let's see, the height of the water is at 5 meters. So let me change to blue to represent water. So we're about here, 5 meters. And so what can we do? Okay, so what we can know is that there is the volume of water in this tank. We know it's losing 11,300 cubic centimeters, right? We're going to be subtracting off 11,300 from the volume. Could we calculate the current volume? We know the volume is going to be 1/3 pi r squared h. So we could put in the 5. We'd have to calculate at 5 feet what that radius is. Remember, we did a little trick on this one though, because we didn't want to have two different. We didn't want to have to deal with the rate of change of the radius and the rate of change of the height. Since we're given the rate of change of the height, what did we do? Is that? Got R in terms of H, or yeah, H in one of those two, by looking at similar triangles. So what we know is that this, we've got one sort of bigger triangle. I guess we could go like this, where the radius is 3 and the height is 9. And then we've got another similar triangle with the height of 5. Or we could just, I think we want to maybe just keep that as H, and this would be R. So since they're similar, 9 is proportional to H, and 3/9 should be proportional to R over H. And then did we solve for H or for R? Can't remember. But anyway, 9 goes into 3, so that becomes 1/3. I'm going to multiply both sides by H, right? So just getting, then I'll put it in, I'll figure out. So we get 1/3 H equals R, or if you want to go the other way, multiply both sides by 3, H equals 3R. Since we know H, we want H in our formula, so we need to solve for R so that we can plug in for R, and it's gone, right? I have to kind of do both. So we want this one. We're going to plug in for R 1/3 H. So then we get our volume formula. H over 3 squared times H. So we're going to get, hopefully I have enough room here, We square the 3 is going to be 9. 9 times 3 is 27. So we're going to get pi over 27 h cubed. Much nicer thing to look at. Oops, cubed, not squared. We got that so far? Since we have things in terms of rate of change, right? The water is rising at a rate of 16 centimeters per minute. We can take the derivative of both sides. dV dt is equal to 3 comes down, so 3 pi h squared over 27. 3 and 9 can simplify, so you get pi over h squared equals 9, right? 27 divided by 3. And the question is, how much water is being pumped into the cubic centimeter per minute? Okay, so what's the change in volume here? What we can see is that we know the height is 5, so this is the rate of change, so we can find dV dt, which is what we're looking for, by plugging in h, 5 for h. So you should get 25 pi over 9. Put that here. Is that our answer? So what? Not quite, because this is the amount that it's rising. So remember, while we're pumping water in, water's being pumped out. So this is the net change. So this is pumped in minus pumped out. So to get the amount being pumped in, what we need to do is take this number plus the amount that's leaking out. So this is the amount, the net result. So if we add on 11,300, this should be our answer. Should work. Again, take a look at this. You might have slightly different numbers than I've got. Take a look at the solution, but that should do it for what they gave us. Well, it's negative, but good question. Because it is leaking out, we would take what's pumped in minus what's pumped out. That would give us the net. So since we've got the net, it's on the other side of the equation. We're adding it. But yes, you're right, it is a negative value, but I guess I should put that in. So the net is equal to N minus 11,300, and this here is what we came up, that's the net result. So we had to bring the 11 over, add it together, and then that'll give us the amount in. Good question. Does that help? Questions? Okay. Yes.
We took the derivative both of the sides. You got dt and dt on the left. Why is it that on the right you didn't take the derivative of h to get dh over dt?
You're right. You're right. That's why I always forget something. Thank you. So yes, when I took the derivative of h, what was the rule I said when you take an implicit derivative? You got to have a marker. I forgot my marker. So on this side, I was taking the derivative of h with respect to time. So when I did it, I should have put dh, dt, dh. That's why the answer probably won't work. So the 5 actually doesn't go into the square, the h squared. Oh wait, 5 does. Yeah, I guess if I would have thought about it a little bit more, they give us the rate that the water is changing, the 6, so that's the dH dt. Well, I didn't use that, and that should have put some alarm bells off. So this also has to get multiplied by dHdt, which is 16 at this spot. Okay. See? Needs a community to get it right. Good, thank you. Yes?
Can you do number 6 on 2.8?
2.8, number 6.
I just didn't know how to like solve like secant squared of x, like can you put a value in
Okay. 2.6, so we'll go. Wait, 2.8. I wanted 2.6 because it'd be easier. Which number?
Number 6.
Number 6. Okay, let tan equal that, or let y equal that, tan of 3x plus 4. Find the differential dy when x equals 1, dx equals 2. Find the differential. Okay. So it's sort of like implicit differentiation. But remember so what we're going to do is take the derivative of both sides. We'll get dy times the derivative of the function dx. So dy is just dy. Derivative of tan 3x plus 4, we have to use a chain rule, right? So derivative of tangent is secant squared. Okay, so those are the ones, yeah. And again, you're going to see the inside stuff unchanged. Got to use the chain rule. Chain rule says the derivative of the inside is just 3, right? So we multiply by 3. I like to put it in the front, but you could put it in the back. Then, oh, thank you. Markers, yes. dx. There we go, yeah.
And then so when you put the x value, I just didn't know how to get an output for like secant.
Oh, so, okay. It's part of the notation is really whacked. It really should be secant of 3x plus 4. The square is on the whole function, is really what it is. We put it onto the secant, so it makes you think I've got to go secant squared and then put it in, but the calculators won't do anything because it's really secant of this stuff all squared. Does that make sense? So when you go to plug in things, you're going to put in 3 secant of 3 times 1. Right, 3 times 1 is 3 plus 4, so you can get secant of 7, and then you're going to square all of this, and then for dx you're going to put the 0.2, and that will give you your dy. Okay.
Is there a secant function on the TI, or do you have to do like one of those?
It might be in the math function, but what I always do is I just do 1 over secant, 1 over cosine.
Yeah.
Is how I do it. Oh, here it is. I know on Desmos they have it, which is nice, but until I get them to allow us to use Desmos, then math, I don't think there's a secant. And they use the cosine, they use the inverse cosine above it, so that's not going to do it. Yeah, so I would actually, when you go to put this in your calculator, I do 3 times 0.2 all over cosine of 7 squared. That's how I would do it. And be sure you're in radians, because it's not real clear that we need to be in radians, but x is not in degrees, so that's the only other choice. Yeah.
Can you do number 9 on this?
Sure. Okay, and then the other one, you just use the other numbers, right?
Yeah.
Number 9. Yeah, the trig one's part of it is there's a lot to kind of remember. The radius of a circular disk It's given us 26 centimeters with a maximal error in measurement. Okay. You're gonna make me think, huh? Okay. We've got a circular disc. The radius is 26 centimeters. Our error in measurement is plus or minus 0.3 centimeters, so it could be 26.3 at the high end, or it could be 25.7, right? Use differentials to estimate the following. Okay, the maximum error in the calculated area of the disk. Okay, so the area of the disk is pi r squared, right? It's not too bad. Let's see how we do this. So use differentials. We're going to take the derivative of both sides. And so we're going to get a is, is our dy. We could think of this as y and x. Sometimes that helps. We got too many variables going on. We'll say, okay, area is actually the y value. The radius I'm going to put as x, just so I'm using familiar variables. So then the differential is going to be dy equals 2 pi, when I take the derivative, right, 2 pi x dx. I've remembered it this time. Or you could do dr if you wanted to, and dA. So that's the differential. The error in measurement is what we use as our dx or our dr, right? Because the radius could change by that amount. What we're trying to find, the maximum error in the calculated area of the disk. And we have a starting value that we're at 26. The relative maximum error, the percentage error in the case. So we could, the maximum error in the calculate. Okay, so using differentials, we should get that dy might be off by as much as 2 pi. We know that x is 26. We know that this is plus or minus, but we'll just, as 0.3, so this gives us the maximum side, the positive one. So it looks like our sort of change in y could be off by 2 times 26 times 0.3 pi. Maximum error. So, and that would be, so if we had the maximum error in the radius, that would be the maximum error we would get for the area. The relative maximum error, so relative is a percentage. So for that, we divide by what the area was supposed to be, right? I think. Yeah. So what is it supposed to be? It's supposed to be, area is supposed to be pi r squared with 26 if we were accurate. So what we're going to do is we're going to divide this, so the relative error over 26 squared pi. Pi's will cancel, you get 15.6 divided by 26 squared. Oops, not cubed, squared. So I get about 0.023, about a 2% error in the area. 0.023. So I could put it over here. And then finally, the percentage error. Wait a minute, the relative maximum error, the percentage error in that case.
The percentage error just be 2.1.
I was going, what calculation do I need? Okay, we got it, yeah, so this is the relative error as a decimal, change it to a percentage, thank you. So much easier than what I was gonna try to, I don't know what I was gonna try to do. I was gonna look at the solution and then I would've got it. Make sense? How many of you guys know someone else either in this class or another class that you study with? Good, you. It's the best way to get through, especially if you've got food involved. Have some fun doing it, listen to some music, whatever, but get together with, it's, you know, make it social. That's one of the, actually, when I was at Oregon State, that's one of the parts of the research we did. I worked in this group, we had, we specifically, we had a class that taught people how to socialize when they're doing their math. And in fact, we'd even have pizza party. We got budgets from the department. They said, what do you need pizzas for? Well, so people have fun, they're enjoying doing math, they'll do more of it. It worked. Who would have known? Just give them some pizza and they'll do better in math. But yeah, work with other, and it's by talking through these things, working together, will get you, you know, we'll all get there. What else? Anything else? Are we? Again, we got some time. That's what I like these ones, is we've got a little day, and then we'll do 3, and then we'll have a day where we just look at that, and then we'll get real serious, and we'll have a real serious review day, and then we'll have a test. So, but the goal is that by the time we get there, you're feeling a lot more confident in the methods through there. And again, a lot of times, yes.
Can we go over 2.5 questions?
You got it. Ooh, trig again, right? Okay. What do they want? This set is variable, visible, okay. Let f of x equal that, find the derivative. Okay. So, let's write this a little bit larger. What do we have here? Do we have product rule? Do we have quotient rule? Do we have chain rule? Six sine of 6x minus 4. So we've got those parentheses, we've got something inside parentheses that's going to indicate a chain rule. There's nothing, well, there's 6 times it, but 6 is a constant, so we don't have to worry about the product rule with this one. So again, what we're going to do is sort of do the chain rule, so we just kind of cover up the inside. It's really, think of it as, as just being 6 sine of x. That's the outside function. What would that derivative be? 6 cosine, but of whatever's inside there, right? So the inside, it's protected. I would say it's like it's got a rubber suit on. It's in a bubble. Nothing can happen to it. But then we got to pop the bubble and make something happen to it. We got to mess with the inside stuff. So we've got to take that derivative of that inside stuff, which is just going to be 6, right? Because the derivative of 4 is 0. So we get a 6 out here. We combine them, 6 times 6. So we're probably the final answer looks something like this, 36 cosine of 6x minus 4. And again, I think do you guys get exactly the same questions? Or okay, yeah, it randomizes them a bit. So sometimes you get a harder one, sometimes you get an easier one. Does that help, though, with what?
Yeah, I think I blanked out. Why did we do times 6?
We did times 6 because that's a good question. What I did is I took this inside stuff here, So let me write that and make it more explicit. 6x minus 4, I took its derivative. Derivative of 6x is 6x to the 0, which is 1. Derivative of 4 is 0. So maybe I do like that. So all that so the derivative of the inside stuff was just 6. So I multiply derivative of the outside stuff times derivative of the inside stuff. And again, yeah, the more times you go through it, talk about it, because sometimes it's, you start doing it, but as long as it's out there, it becomes second nature. And that's kind of what they expect you to do in these classes. It doesn't happen quite as quick, but at least the good news is we don't have a 7-week class. Like I teach a session A, session B pre-calc. They're doing, and it's just so fast. It's just not. I could go with about an 8-week class, but I don't know, 7.5 or 6.5 weeks is just like too short. And Phil, some of my students are in Florida, because of it's an online course. So they're already contacting me. They're going through some hard stuff right now. So think about got friends over there. I lived in Florida for a little bit, New Orleans. I've been through a couple hurricanes. Fortunately, only a little bit of the house was damaged. Banana tree was put on the neighbor's roof, so that was okay. Peach tree got blown over, but we survived. This one looks like it's going to be pretty bad, so keep them in your minds and thoughts. Anything else? A lot more straightforward than limits, right? I think that limit thing is kind of, but anyway, we're doing good. We're on track. Keep making good progress. Remember, I do have office hours right after this. If you want, you can just follow me there or meet me there. I'm there till 5:30ish. I have a class at 6 that I head off to afterwards. And some of those students come a little bit early, but feel free to drop in and you can. Yes?
Did you say you're changing the due date?
Yes, and I will, if nobody comes, well, as I get time, I'll do that at the latest. I'll do it when I get home. Because otherwise, if I wait till tomorrow, I'll forget. But yes, I will move all the homeworks to just before the test.